purpose of this video is to show some of the features in Excel that we can use to do confidence intervals. Now, some features are going to be built in, specifically if we're looking at confidence intervals for mean. Others we're going to have to build. Specifically, we can use the same concepts here to find out what sample size we would need if we wanted a particular margin of error for our confidence interval. And also we can build a template for finding margins of error and confidence intervals for proportions. So that's what we're going to do. We're going to do a total of 4 tasks. First, we'll look at a confidence interval for a mean, then for a proportion and build a template that we can use for doing that calculation. Then we'll build a template for how we can find necessary sample sizes, and then we're going to make some modifications to that template if we happen to end up with a sample size that's too small for the methods that are in the original way that we're going to try it. All right, so let's go ahead and get started. So we'll start with the confidence interval for a mean. So I have here a spreadsheet with a few pieces of data. It looks like a total of 20 data points for miles per gallon for some kind of vehicle. Looking at how high these are, it's a fairly fuel efficient vehicle, getting somewhere between, looks like 35-ish to 50-ish miles per gallon. So the reason we use a confidence interval first, remember that's whenever we are trying to use a sample to estimate the mean of a population. We can also use this for other statistics as well, but we'll focus on a mean here. So the key is that the sample's mean does not necessarily match the population mean exactly. In fact, it's almost certain not to, right? There's something specific about this sample that is going to be at least a little bit different than the population as a whole. So that's why we add a margin of error to our sample mean. So let's get into how we would do that. Right, so I'm going to use one of the built-in tools that makes this really quite easy to do. So first, you need to access the data analysis tool pack. If you haven't already activated that, it does come in every installation of Microsoft Excel. You just have to activate it, right? So you'll want to go into File, Options, Add-ins, and then Manage your add-ins, activate the analysis tool pack, and you're good to go. All right, so let's go ahead and get started here. So I'm going to open up the data analysis tool pack, and that gives me this list of tools that are available. I want the descriptive statistics. I'm going to click OK. So I have my input range. This is where my data is. So I'm going to select the data. I'm going to include the label here. That's not strictly necessary since I'm only dealing with one data set, but I think it's good practice to do that in general. So I need to tell then Excel that there is a label in the first row. Otherwise, it will give me an error because it will try to include that MPG label when it's trying to calculate things. Where I want the output to be, I'm going to keep it in the same spreadsheet. So I'm going to say output range. I'm just going to put it here starting in C1, and then it will build a table starting in C1 and then go from there to the right and down. In that table, I'm going to need the summary statistics. That's things like the mean, the median, and so on. And then I also need confidence level for mean. This is what's going to activate the confidence interval calculation. And then we click OK. So you can see it gives us a number of statistics here. Right? So we have mean, standard error, median mode, standard deviation, etc. What I really need, though, for what my purpose is today is I need the mean. Right? So that is going to be the center point of our confidence interval. Right? And then this confidence level 95%. So this is saying if we're using a 95% confidence interval, which is what we decided to do, really because that's standard, then this is what the margin of error would be. So then to find our confidence interval, what we need to do is take the mean and add and subtract that margin of error. So I'm going to go ahead and do that over here. I'm just going to make 2 labels here, so one for the upper bound, one for the lower bound. And the formula here is really quite straightforward. That is, for the upper bound, we take the mean, which is located for me in D3, and then add to that margin of error, which is confidence level 95%, this 2.066255. Right, so there's my formula. Mean plus the margin of error gives me the upper bound. Then for the lower bound, same kind of idea. Take the mean and subtract the margin of error. So there's my formula. Mean minus the margin of error, and that gives me my lower bound. So how we would interpret this is we'd say that we are 95% confident that the population mean falls between 41.10 or so and 45.24 or so. All right, so that'd be our interpretation here. Now, certainly you can do other levels of confidence. Sometimes you'll see confidence levels as low as 80%, sometimes as high as 99%, or even sometimes a bit higher, and that will simply change how large your margin of error happens to be. The way that I typically explain that is that, say you're trying to guess my age, and you say you want to be 50% sure you get it right. In that case, you're going to give a pretty narrow range. You can look at me and make a reasonable guess within a few years, probably. Right? On the other hand, if I say, I want you to be 99% sure that my actual age is in the range you give me, right, then you're going to give me a much wider range. Right? You have to do that in order to be 99% sure. Because maybe, well, I'm probably not somebody that looks unusually young or unusually old, but I might be. So if you want to be 99% sure, you give a wide range, you effectively cast a wide net to make sure that you catch that population mean. On the other hand, with a relatively small level of confidence, then you can have a much narrower range. All right, now there are a couple other ways that we can do this. All right, so this is using that, I like the descriptive statistics because it gives us so much at just with a couple clicks. However, all of these do have formulas that you can use or combinations of formulas that you can use. So let's say that we were just wanting to use formulas. So in that case, we would need two things. First, we need to calculate the mean, and then we need, again, that margin of error. Right. So for the mean, the formula here is just average. So average, and then you would select your numbers. There we go. And here we go. As you can see, it says 43.2, so it does show, it seems a slight difference between these two. That might possibly be rounding error or something like that going on here. I'm honestly not positive. Actually, let's see if I can adjust the number of... Yep, that's exactly right. So once I added an extra decimal point, then we see they in fact do match. For the margin of error, the formula for this is just confidence dot t. Technically, we'll use a t-distribution here. The t-distribution is the technically correct one if you're doing a confidence level for a mean, where the standard deviation for the population is not known, so you're estimating it based on your sample. Right. So now what typically happens is that if you have a really big sample, the t-distribution and the normal distribution look really similar, so we'll often default to the normal distribution in that case just because it's close enough. But it is technically correct to use the t-distribution in that case. All right, so our alpha, what that is, alpha is just the term they use for 1 minus your confidence interval level, your confidence level for that interval. Right, so if I want a 95% confidence interval, my alpha would be 0.05. And then the standard deviation, that one I'm going to have to calculate by the formula STDEV dot S. So it's standard deviation, the dot S indicates that it's for a sample. Right? And then we would select our data again here. The last thing that we need for this formula, see it says is the size. For that, the formula would be count. C-O-U-N-T, and then again, we will select all of our data. So that counts how many numbers are in that range. All right, so that would be what our formula would look like. So we select what our alpha is based on our confidence level. The standard deviation it will calculate for us, and it will also count the number of observations in our data. And plug all of that into confidence.t and give us the standard of the margin of error. Notice the margin of error here and the margin of error here do perfectly match because really underlying this descriptive statistics is that same formula. So this would also work. You could use these then, add and subtract as necessary to get your upper and lower bounds. Okay. Now let's move on to the second task. The second task is to construct a confidence interval for a proportion. Now, unfortunately, there is not a good built-in way to do this inside of Excel, but we can use some of the formulas that are in Excel and just build a template that will work for us. So we're going to need two things. So first, the number of successes, and then the number for our sample size. Right, so the way that we think of proportions is that we're looking at a sample and trying to decide what percentage of the observations that sample have some trait we're looking for. Right, so that trait might be something like, say, gender or race or something like that is not unusual, or say people who prefer a particular brand of toothpaste over another, right? So all of these we'd consider to be successes if it has the trait we're looking for. So this one, we're just going to have to input based on the data. Same thing for the sample size. This will also have to be input based on the data. Now the things we can calculate. The first is what we call the sample proportion. There are a few different ways that that gets denoted. I'm going to use p prime simply because it's easy to type. Sometimes this is also referred to as p hat, or we'll put, basically it looks like a caret above it, so it looks like the p is wearing a hat. But I'm going to use p prime here. So the formula for that one, if you're putting this formula in, do not include the apostrophe. I'm just including it so that you can see the formula. It won't go away after I'm done typing. Right? So this is going to be b1 divided by b2. So all we do, take the number of successes, divide by the sample size. That tells you what percentage of your sample has that particular trait. The next thing we need is a standard deviation. The standard deviation, in order to calculate that for a proportion, we can't use the built-in standard deviation formula. Instead, we're going to have to program it by hand. Fortunately, it's relatively simple, in that you take the square root of your proportion, which is located in B4, okay, multiply that by 1 minus that same proportion. And that would be your standard deviation when you're dealing with a proportion. Okay, so it's square root of your proportion times 1 minus your proportion. And the next thing we need, and the last thing we need really until we calculate our upper and lower bounds, would be the margin of error. To keep widening this thing, it's not quite wide enough yet. There we go. All right, so the formula here, we're going to use the other confidence interval formula. So it's confidence.norm that tells it to use a normal distribution. The inputs here, though, are exactly the same as before. So we'd have 1 minus our confidence level to give us the alpha. And then we'd also have B5. B5 gives us the standard deviation. And then finally, B2 for the sample size. So it wants to know what is the size of the sample. B2 would tell it that. Right. So then that's ready to go. The last thing we need is to calculate the lower bound and the upper bound. For that, very much like we did mean minus the margin of error, here we're going to do mean, which is in B4, and subtract off the margin of error in B6. And then same idea for the upper bound, but instead of subtracting the margin of error, we add it. And there we go. All right, so now let's go ahead and actually use this in an example. Right, so let's suppose that I'm interested in what proportion of romance book readers are men. Right, so I take a sample of 100 people who read romance novels, right, and we find out that of that sample of 100 people, 15 self-identify as being men. Right, so in that case, the number of successes, that'd be the number of men in our sample, would be 15. And the sample size would be 100. Right, so we asked 100 people, 15 said they were men. Right, now it's a matter of activating the, so I need to take all those apostrophes out, so it does actually read it as a formula instead of as the string of characters. Right, so my proportion is going to be 15%, so 0.15. Standard deviation is going to be, see, it's 0.357071. And now this confidence.norm, I do have to put the confidence level in there first before I convert this. So it's 1 minus, I'm going to do a 95% confidence interval because that's pretty standard. So 1 minus 0.95, and then now I'm ready to remove that apostrophe. So it gives me a margin of error right around 7%. And then finally, activate the last two by taking these apostrophes out. So what we've just found is that we are 95% confident that somewhere between 8% and 22% of romance book readers are men. The third task, then, we want to find a necessary sample size. So here, let's get into a little bit of the math. Right, so the underlying math, right, for the margin of error, it's really a combination of three things. That is, one is what we would call a z-value. The z-value is based on your confidence level. Right? The next thing, or that could be a t-value, depending on the type of calculation you're doing and how large your sample size is. But for our purposes, we're going to use a z-value, so it's based on the normal distribution. Then we multiply that by the standard deviation from our sample and divide it by the square root of our sample size. So with this formula, what we can do, we can actually, if we have a margin of error in mind, and we know the confidence level we want, so we know the z we want, and we have some guess what the standard deviation is, we can actually plug all of that in and solve this equation to find what our sample size would have to be to get our desired margin of error. Right, so we can rearrange this all to get a different formula. So let's go ahead and set up the template to do this. Right? So we need those three elements. We need the z-value, we need our standard deviation, that is based on our best guess, because we haven't actually gathered the sample yet. We need our desired margin of error. And then we're going to use those three things to calculate our desired sample size. Right? So first, for the z. So this is based on the standard normal distribution. So what we're trying to find is effectively a multiplier. That we're going to multiply the standard deviation divided by the margin of error, or I guess it would be multiplying the standard deviation divided by the square root of n to find what our margin of error is. Right? So we need to find that multiplier, and we do that based on the standard normal distribution. So here's how we do it exactly. So we take the absolute value of norm.inv. What norm.inv does is it inverts the normal distribution. So let me get a little bit further to explain exactly what that means. The next thing we need in here is 1 minus our confidence level. Then 1 minus the confidence level divided by 2. So actually I need to put another set of parentheses in here for this to be correct. Right, 1 minus confidence level, then you take that thing divided by 2. The next thing would be your mean, which is 0, and standard deviation of 1. That's because we're dealing with what we call a standard normal distribution. The standard normal distribution, just the term standard, means that it's a mean of 0 and a standard deviation of 1. All right, and then we close out all the parentheses. So what this is going to do, right, so norm.inv is going to look at what is the value that you're going to need to get a certain percentage of probability to the left of that value in the distribution. Right, so specifically it'll be 1 minus your confidence level divided by 2 is what we're looking for. So in our case, since we're talking about a 95% confidence interval, that'd come to 2.5%. Right, so what that means is whatever value this gives us, it's going to be such that 2.5% of our data falls to the left of that value. It's also going to be true that if we take the absolute value of this, so it would be a negative number, take the absolute value that makes it positive, then 2.5% of the data will fall to the right of that value, which means between these you're going to have 95%, which is exactly what we want. Right? So I'm going to go ahead and plug in my confidence level here. Right, so it's absolute value, and this confidence level I want 0.95 because we're using a 95% confidence interval. All right, and then hit enter. All right, now you notice here I've said nothing about our specific data. This is a standard value, this 1.96 or so. If you're dealing with a 95% confidence interval and you can use the normal distribution, which means either you're dealing with proportions or you're dealing with a fairly large sample and you're dealing with means, then this is going to be close enough. In that case, 1.96 is the number we're going to use. And you're going to find this number show up quite a bit when you do confidence intervals and also when you do hypothesis testing. The 1.96 is a very common number that you'll find. Okay. The next thing would be the standard deviation. Now this one is going to be based on our best guess. Right? Or if you're using proportions, if you have a guess what your proportion is going to be, it's going to be the square root then of that proportion, 1 minus times 1 minus the proportion, the same formula we used in the previous task. Now, if you have absolutely no clue what your proportion is going to be when you're dealing with proportions, then just put in 0.5, because that is going to give you the largest standard deviation, and therefore it'll be the largest sample size you would need to hit your desired margin of error. And the margin of error here, this is something you choose. So this is really based on whatever your desired margin of error is. So finally, the calculation that gets done is going to be this n. So to calculate the n, what we do, we're inverting that formula from before. Right? So what it'll end up being is, let me put that apostrophe in there so that this won't go away as soon as I'm done typing. So is your b1, that is that z, multiplied by your standard deviation, which is in b2, and then we divide that by the margin of error, and then square the whole thing. And so if you take that original equation from a couple minutes ago, right, and then you solve it for n, this is the formula you end up getting. Right, so let's go ahead and put an example in here. Right, so let's suppose for the moment that what I'm trying to do is I'm trying to find, I want to get a good guess of the defect rate for say the production of ball bearings or something like that. Right. Now, I want the margin of error when I'm measuring this defect rate to be no more than 1%. Right, so I'm going to put that in. So my desired margin of error is 1%, which would be 0.01 in decimal terms. The other thing I need is a guess as to the standard deviation. Now here, because I'm talking about proportions, the defect rate would be what proportion of our product has defects in it. I can just use the formula that I have here, that square root p times 1 minus p. So I'm going to go ahead and do that. So I'm going to change this. So it's equal to square root of p times 1 minus p, and then I need to plug in for p whatever my best guess is. Let's say that I think it might be 10%. So I'm going to put in 10%, or 0.1 for my p's here. And then hit enter. All right, so that gives me a standard deviation of 0.3. Now all of these are numbers, b1, b2, b3, good. So this formula will work once I remove that apostrophe to activate it as a formula. And there we go. Now another point about this is that you should always round this number up. So it isn't possible to have a sample size of 3,457.313. The 0.313 doesn't make any sense because you're going to have an integer, actually a whole number for your sample size. Right, so another thing we can do, just a quick modification. Right, I'm going to tell this to round it up. So round up that formula we had before, and the number of digits, 0. Num digits tells it how many digits after the decimal point we want, and we don't want any. So this is going to take anything that is not a perfect integer and we'll round it up to the next one. Right? So there we go. So 3,458 is what we want. Right, so that would complete this task most of the time. And then we can also play with this. Say, well, what if I want a larger margin of error? What if that's okay if it's 0.1? And find out we would need a much smaller sample size. On the other hand, if it needs to be much smaller, we would need a much larger sample size. Okay. All right. The next thing you can run into is that I mentioned before this formula. Okay, so this is all assuming that your sample size is going to be at least 30. If it's at least 30, then the normal distribution that we're using in this formula for that norm.inv is going to be close enough that this is going to be valid. If you're dealing with proportions, as long as you have at least 5 successes and 5 failures in your sample, the normal distribution will be close enough to be valid. But what if that's not what happens? Specifically, what happens if you're dealing with a mean, but you end up with a sample size that's relatively small? And this is something that can happen, and it can happen fairly easily. Well, in that case, the normal distribution is no longer valid, and we're going to have to replace this. So here's how we do that. Right, so we need to make a modification to this formula. So if we're dealing with, we end up with an n and it says something less than 30. 30 is about the cutoff where we get close enough. If the n is less than 30, we're going to have to make some adjustments. So here are those adjustments. So first, where it says norm.inv, we need to replace that with t.inv. The t distribution is what we're going to be using. Right? And then we no longer need this 0 and 1. That's not part of the t.inv formula. You can see it needs the probability, so that 1 minus 0.95 divided by 2 will still be valid. Instead, what it wants is the degrees of freedom. So your degrees of freedom is really just your sample size minus 1. Right? So I'm going to put that in as n minus 1 right now. Right? And then you can see where we're going to have a problem, because this is going to be a circular reference. So it's no longer z, it's going to be t. Our t is based on our sample size, and then we use the t to figure out our sample size. Right? So in practice, the way that we will do this is we guess what our n is going to be, and then we see if our n is consistent with that. Right? So let's go ahead and change some of these. Let's make the standard deviation a little bit higher. Let's make it 1. So our margin of error is 0.44. All right. And then I'm going to put in a number here. Let's just put in a number of 30. So 30 would be enough that we could go ahead and use that normal distribution. And here's what we find. Right, so if we put in 30, right, it says the n should be 22. Right, well, that's not consistent. So we need to go back and change our n here. So rather than having it be 30, I'm going to change it to 22 and see what happens. So 22. Now it says it should be 23. So that's not consistent again. So we need to change the 22 to 23 and see if we get something consistent. Ah, excellent. Right, so 23 in, 23 out. It's all self-consistent with itself. Now remember, this is with having that round up in there. Right. So now this is all okay. Now, there is another way to approach this problem and solve it, which kind of allows us not to have to go back and do that repeated guessing and checking effectively is what we're doing. Right? So instead, we're going to do this. We're going to have different sample sizes. Let's say we start with 2, and then we can go all the way up to, let's say, 2, 3, all the way up to 30. I'm going to drag this down, so we're going to have lots of lines, more lines than I can display at once. Yeah, that's okay. All right. So these would be the n that we're putting in as a guess. Right? And then from that, we're going to calculate what our t would be using this formula. All right, so let's go ahead and take that formula, and we'll put it in. So I'm copying this formula down, equals this thing. Hit the wrong button. Okay. So instead of it being 23 minus 1, it's going to be our n, which we have in column A. So in this case, it would be A8 minus 1. Right. So this tells me that if I put n of 2 in, it gives me a t of 12.7062, and then I can put n prime. That would be what it says based on this guessed sample size, what our sample size should actually be. To get that, I'm going to use the formula from here, but I'm going to have to make some modifications to it. And then we come down here, put it in, right? So the big thing here is that I'm not using this t anymore. So I'm not going to want to refer to b1. I want instead to refer to b8. So I want to take the t that goes into the formula right, from the line that I'm in. And then the b2 and b3, I want to make sure those don't change when I copy this formula down. So I need to put these as absolute references. That means adding the $ in front of the b and the front of the 2. You can also hit F4. Will automatically do that for you. Right, so just have your cursor inside or right next to the thing you want to change to an absolute reference, and then F4 will do it. Okay, there we go. So this is saying if I start with a sample size of 2, then the sample size should actually be 834. So clearly not consistent. Right, and then we can just take this and copy it down. So I highlighted both of these. I'm going to select here. So you'll see your cursor change to what looks like a black cross, right, and then drag it down to fill in our table. And what we are looking for is where we're going to have the n and the n prime be the same number. So we scroll down a bit. So 14 gives us 25. Okay, that's not the same. Oh, this is the same. So 23 in, 23 comes out, and that's exactly what we found before. So this is just another way of solving that same problem. Okay. All right, so that should wrap that up. So now you have some idea of how we can use both the tools that are built in and also how we can build templates inside of Excel to figure out what confidence intervals are, and then also to use that knowledge to figure out if we have a target margin of error, what sample size we need in order to hit it.